Hello, today's method is the method of the steepest descent, and first of all, let's repeat the basics of the theory on this method. It is applicable just for a positive definite operator in the operator equation of the first kind, AU equal to F, and it's just applicable in the case of bounded operators, therefore not in the case of differential operators. So we have the operator equation of the first kind, AU equal to F, and as we know, there exists some element U0 minimizing in a Hilbert space H the quadratic function of Fu equal to AUU minus 2Fu, where brackets denote the inner products in H. This fact that the element U0 minimizes this functional makes possible the following geometrical imagination. The functional f assumes for every u from H a certain value. Geometrically, this functional can be imagined as a certain surface above the space H, which assumes its least coordinate precisely for u equal to u0. Starting from an initial point, we now desire to approach as rapidly as possible the point for which this coordinate is minimum. We proceed along the surface, namely in the direction of the surface steepest descent. Let's choose a certain element U0 from H, and if U1 from H, and if AU1 equal to F, then the problem is solved. U1 is equal to 0, U0 then. In the opposite case, we have AU1 minus F be not equal to 0 in H, and the element U1 is considered as the first approximation of the desired solution. Let's find in H such an element V1 for which V1 is equal to a U1 minus F, and consequently it is still for the norms of these elements. And then for the first approximation of for the first variation of the functional, we have to find such number t and knowing number t, to find such element V1, which supplies the maximal value of the first variation, or the maximal value of the tangent on the curve, which is a line belonging to some surface, this surface above the space H. Then we have the next FU1 plus T1 equal to FU1 plus this. Calculating the first derivative, we have this relation, and substituting t equal to 0, we have the first variation of the functional equal to this expression. But we know that V1 is equal to AU1 minus F. It follows from here. And then substituting 0 instead of the first variation of the functional into this relation, we can find first approximation to a number t. T is equal to this over this one. As the second approximation of the solution, we take the element U2 equal to U1 plus T1 by V1, where V1 is AU1 minus F. If AU2 is not equal to F, we continue further in the same manner, that is, we construct the element V2, the second approximation to the function V, AU2 minus F. And U3 is U2 plus TV by V, T2 by V2, where T2 is, like here, minus V2 by V2 over AV2 by V2. And that's all on the basics of this method. Now we have some exact example. In the space H equal to L2 from 0 to pi, consider the integral equation, this one, where H belongs to L2 from 0 to pi. And first of all, here is shown that the operator AU in the left-hand side of this equation is positive definite. It is obviously symmetric in L2 from 0 to pi, and further we can show its positive definiteness. So we can use the method of steepest descent to solve this equation. We have the space L2 in the domain from 0 to pi. These are the bounds of our domain. We put the function h from x equal to unity in our example. Now we create space net on our interval from A to B. And we do the same for the right-hand side function of this equation, h from x. We denote its discretized values as coordinates of the vector f. So fj is equal to h from zj. And let's put the number of approximations in the method of steepest descent equal to 10, and even 11 as we start with 0. So according to our algorithm, I start with 0 subscript. Here is from 1. That's the difference. So we first of all, let's put the first approximation equal to unity. Then we have n approximations of our solution, and we calculate each approximation for every point of our space net, of our net, in the bounds of the interval from A to B. So first of all, we have to calculate the operator A, this one in this case. So as we start from unity, but the subscript is from 0, we denote subscript here I minus 1, the point j. It is equal to u I minus 1j minus this coefficient by this discretized analog of the integral, sine z j x outer coordinate plus zk s inner coordinate, that is under the integral, by u and by the differential zk minus 1. So corresponding function v I minus 1j is equal to au minus f. And now we have to calculate also av I minus 1j. So it is according to this expression, v instead of u from x for v, I minus 1j minus coefficient by this integral, and it is the same, but here we have v instead of u. And t approximation, another approximation to t is equal to this relation minus this inner product, that is integral v by differential by this inner product, that is this differential analog of the integral. And we calculate the next approximation to the desired function u. Ui is equal to ui minus 1 plus ti minus 1 by vi minus 1, and further. Till the number n big. That's our solution, and now we draw it for all the approximation at this graph. The last approximation is in blue color. And let's compare it with the solution of this problem from the textbook. Here the solution is given by this formula, so let's use it and let's construct the graph for this function. So as we can see, we have very closed functions. So we have solved this problem. The second problem on the method of steepest descent is more complicated and has some physical essence, some physical sense. So let me open it. Just a sec, please. Now consider a linear antenna in the form of a straight rod of length 2L, and we direct this z-axis along the rod. So we have and its length is 2L. So we had the 0 point at the center of this rod. Here we have 0 point. Suppose that a current of amplitude J from Z, varying with the time according to the law, exponent law, is produced in the rod with the aid of special devices. This current causes an electromagnetic field symmetric about the Z-axis. Here we have Z. About the Z-axis in the space surrounding the rod. The electric and magnetic field intensities caused by the current J from Z and the intensity of the radiation of the antenna are determined by that current. That is, they are functional: A E from J, A H from J, and A M from J. Let Q denote a plane in which the axis of the rod lies. Let's draw a circle in Q of radius r much greater than both the wave length lambda and the rod length 2L. So here we have a plane. Plane Q. And then at every point, and let's draw a circle in Q of radius r much greater than the length of the rod. Let's make it schematically. So it's our circle. Then, at every point of that circle, the magnetic field vector will be directed perpendicularly to the plane Q. Its magnitude will be a function of the radius r and the angle theta between the z-axis and the direction from the midpoint of the rod to the point of reception. Let's create here reception point. Its relative value, for example, to its value at some point of the circle, is a function only of the angle theta. Between the z-axis and the direction from the midpoint of the rod to the point of reception. So let's create this angle. Here we have theta. Found Greek symbols. So let it be simple. Theta. This angle. The function p from theta is called the directivity pattern with respect to the magnetic field intensity, the electric field intensity, or radiation flux. In the case of a complicated configuration of the antenna, the directivity pattern A from J will be a vector function of the two spherical coordinates, theta and phi, of the reception point. In the case of a linear antenna of length to L, the connection between the current J from Z and the directivity pattern P from theta is expressed by the next formula. So we have the integral equation of Fredholm of the integral equation of the first kind. It's the same, where k is the frequency omega by c, the speed of the light, is the wave number. C is the speed of light. The direct problem in antenna theory consists in determining the directivity pattern P from theta from a given current J from Z. That is, in calculating this function. The inverse problem in antenna theory is usually the problem of finding the distribution of current J from Z generating a given directivity pattern P from theta. For a linear antenna, in our case, this problem consists in solving a Fredholm integral equation of the first kind, this one, in J from Z. J from Z is desired function. This problem is ill-posed and has a solution only for a very restricted class of right-hand members, P from theta, that is, for realizable directivity patterns. Now we have to find the current J from Z in the linear antenna for the directivity pattern P from theta equal to exponent I by theta, where theta is from minus pi to pi. And here I have changed the lower bound to 0, not from minus pi, but from 0. So here is the bounds of our interval for theta angle from 0 to pi. It's a frequency of the waves, electromagnetic waves, and it's the speed of light. It's the wave vector. And consider the coordinates along the rod from minus 1/10 to 1/10 meter of meter. As we have here 0, so here minus L, and here is plus L. And our directivity pattern is given by exponential function to the power of I by theta. We are complex field. I is imaginary unit. So for a real part of our complex number, we have this distribution. For imaginary one, it is 1. We create two nets, space nets, for the angle coordinate theta, from theta 0 to till theta m, and we do the same for the coordinate along the rod from z0 till zm, and we discretize the right hand side of our equation. F is equal to V from tau j. Tau j is the coordinates of the vector tau, discretizing our angle theta. We are going to use 20 approximation to the desired solution and realize this algorithm again. We put the first approximation, then we calculate, taking into account that we start with 0 subscript au I minus 1. Here we have this function signed by this integral. We calculate v I minus 1 as u I minus 1 minus f. Then we have to find the operator a v I minus 1. It's the same, but here we have v instead of u, and we calculate t I minus 1 using the same formula as it was at the previous case, previous task problem. And we calculate the next approximation to the desired function using this relation. ui is equal to ui minus 1 plus ti minus 1 by vi minus 1. So we have the next solution, and the last approximation is given by this blue curve. Dependent on the length of the rod, its imaginary part of the desired function and its real part. So we have solved this physical problem for electromagnetics 2 using this method of the steepest descent. And this problem may be even ill-posed. So we complete with the method of the steepest descent. Thank you for your attention, and goodbye.